All right, let's talk about chance. We're going to pull back the curtain on probability and demystify the rules that kind of govern our lives, whether we realize it or not. You'll see how the math behind something as simple as a snooze button can actually help us understand the real stakes of a critical medical test. Okay, so let's just dive right in with the problem I think we've all faced. You hit the snooze button. Just once, right? Maybe twice. But what does that little decision actually do to your odds of being on time? It turns out the answer involves a really simple but incredibly powerful mathematical rule. So to figure this out, let's meet Shannon. Her morning routine is going to be our little case study. Now, Shannon hits that snooze button on 60% of school days. And to solve her dilemma, whether she'll be late or not, we first need to get a handle on a basic rule for multiplying odds together. And that brings us to a really foundational concept, a key tool for figuring out the chance of two things happening one after the other. It's called the general multiplication rule. Here's the core idea, and honestly, it's pretty intuitive when you think about it. For two things to happen in a sequence, it just makes sense that, well, the first one has to happen. And then, assuming that first thing is a done deal, the second one has to happen. It's all about chaining events together logically. Now, here's what that looks like in math terms. It might look a little intimidating, but trust me, this little equation is incredibly powerful. It lets us calculate the probability of two related events, let's call them A and B, both happening. So let's break down what each of these little pieces really mean. Okay, the most crucial part of this whole thing is that second term, P of B, vertical line, A. This is called conditional probability. It's not just the probability of B happening out of the blue, it's the probability of B happening given that A has already happened. That little vertical line, that's the key to the whole rule. It's everything. So let's put this rule to the test with a quick example to see how it works in the real world. We know that about 55% of high school students play a sport, and of those specific students, only about 6% go on to play in the NCAA. So what are the odds that any random student you pick plays a sport in high school and goes on to play in the NCAA? First up, we take our P of A, the probability of our first event. In this case, that's the 55% chance, or 0.55, that a student plays a sport in high school. Pretty simple. Then we grab our conditional probability, the P of B given A. This is that 6% chance, or 0.06, that an athlete makes it to the NCAA, but remember, it's given that they were a high school athlete to begin with. Now we just plug those numbers right into our formula. 0.55 times 0.06 gives us 0.033. So what does that mean? It means there's only about a 3.3% chance that any random high school student will both play a sport and go on to play in the NCAA. Okay, so now that we've got the rule down, let's circle back to Shannon and her snooze button problem. To really tackle this, we're going to use a fantastic visual tool. This is a tree diagram, and it is the perfect way to map out a sequence of events like Shannon's morning. It lets us see every single possible path and what the probability is for each one. It just makes it all make sense. First, we map out her initial choice. As you can see, there's a 0.60 probability she hits snooze and a 0.40 probability she doesn't. That's our first set of branches on the tree, the first fork in the road. Next, we add the second stage. And notice this. This is really important. The probabilities on these new branches are conditional. So, if she hits snooze, there's a 70% chance she's on time. But if she doesn't hit snooze, that chance of being on time jumps way up to 90%. Each path has its own outcome. So what if we want to find the probability that she hits snooze and is late? Well, we just follow that specific path on our tree and multiply the numbers along the way. We take the 0.60 chance of hitting snooze and multiply it by the 0.30 chance of being late given she snoozed. That gives us 0.18, or an 18% chance. Okay, so we've got these awesome tools now, the multiplication rule and tree diagrams. Let's apply them to a situation where understanding the odds is absolutely critical, and where our intuition can really lead us astray. So I want you to really think about this. A woman over 40 gets a positive result on a routine mammogram. What does your gut tell you the probability is that she actually has breast cancer? Like 80%? 90%? Just hold that number in your head. Now, to solve this, we have to ignore our gut for a second and just look at the facts. First, the disease is pretty rare. Only 1% of women in this group actually have it. Second, the test is quite accurate for those who do have cancer. But third, and this is the absolute key, there's a 6% chance of a false positive for the 99% of women who are perfectly healthy. This table makes everything so much clearer. Let's imagine we have a group of 10,000 women. Out of those 10,000, we'd expect 100 of them to have cancer and 9,900 not to. Now look at that positive test row. Of the 100 women with cancer, 97 will get a correct positive test. But here's the kicker. Of the 9,900 healthy women, 594 will still get a positive test, a false positive. That means a total of 691 women get a positive result. And here is the shocking result. Of those 691 women who got a positive test, only 97 of them actually have cancer. You divide 97 by 691, and you get about 14%. Yeah, just 14%. That's a surprisingly low number, and I bet it's way different from the number you had in your head a minute ago. So why? How can this be? It's because the disease itself is so uncommon. That small 6% false positive rate gets applied to a massive group of healthy people. And that generates a huge number of false alarms, so many that they totally overwhelm the true positive results from the much, much smaller group of people who are actually sick. So from snooze buttons to mammograms, we've seen how the real math of chance actually works. So what's the big takeaway here? How should this change the way we think about probability in our own lives? Well, it really boils down to three key things. First, we've got the general multiplication rule in our back pocket now, our go-to tool for events that happen in a sequence. Second, we saw just how powerful tree diagrams are for visualizing complex problems and making them easy to solve. And maybe the most important lesson of all, we learned that for rare conditions, a positive test result can be surprisingly uncertain, all because of the hidden power of false positives. And that leaves us with a final thought to chew on. Now that you've seen how easily our intuition can get probability wrong, where else might this be happening? What other things that we kind of take for granted as certainties in our lives are really just a complex and totally fascinating game of chance?